Thank you, Dr. Sen, for inviting me to deliver a talk in your FDP program. Let me share my screen first.
Okay, so you can carry it, sir.
Uh, just one second. I hope you can see my screen.
Yes, sir. We are able to see your screen, sir. Sir, I would like all the participants to switch on your camera for a while, just to take a snapshot for the proof of this session and for attendance purpose also. Yeah, sir. You can carry it. Sir. Thank you participants for you can switch off your cameras.
Uh, okay, thank you. Thank you very much. So good morning, everyone. Good morning, all faculty members of NIT Durgapur, as well as other colleges, those who are attending this FDP, and the research scholar and student. So the title of my talk is Understanding Neural Mechanism in Cognitive Processing and Loading. So in this talk, I'll cover few of the fundamental things. Then I'll extrapolate my talk towards the cognitive loading problem. And I feel that this is the FDP in which you need to learn. So, so if I'll talk about the cognitive processing, if I'll ask you, what do you mean by cognitive processing? Because this cognitive processing is a very, very buzzword, I can say, in today's world, because we know that we all are interested in artificial intelligence. We all are interested in, let's say, robotics. We all are interested in this edge computing. And everywhere you will find the word called cognitive. Because when we are talking about artificial intelligence, then the first things comes the natural intelligence. Natural intelligence, people talk about the natural intelligence, definitely this kind of intelligence you might get from different organisms in this universe, from an ant, people start from ant or bacteria to the human being. And definitely the humans are the most intelligent. And the important part of intelligence is called the brain. You know this, the brain and the spinal cord, they create all this interesting thing around us, and for which we are intelligent. And in this intelligence, in this world called intelligence, there is another term which is very closely associated with the cognition. uh, so the first question comes, if I ask all of you that have you seen any AI system? Definitely, I'll get the answer from you that yes, uh, that you have already seen the AI system. And definitely, if I'll ask you, give me some examples, you can easily give some examples, like Alexa, like autonomous vehicle, like Siri, n number of examples you can give me. But if you'll ask me the same question, that have you seen any AI system? My answer would be no. And in addition to that, I might say that in next 15 years or 20 years, I won't be able to see any AI system. So the question is why? Then if you are saying this Alexa or this Siri, they are all AI system, then why I am telling that I have not seen any AI system? Because because if you will try to understand the real intelligence, then you can understand these questions better. Let's say when we talk about, when you discussed about intelligence, because intelligence is a very debated issue, that how will define intelligence, that how our sensory modality they work, and based on that, can I tell that I'm intelligent? No, definitely not. So on top of this question, another thing comes called the consciousness, right? And cognitive processing, this cognition is another part of this intelligence, that how our brain process the information and how it can create the mental map, or how it can create all these wonderful things which is happening in our life. Just imagine in the morning you wake up, and when you wake up and you just uh, went outside to your home and you see this beautiful world, you can hear the beautiful sound, right? So the question is, who is doing all this kind of beautiful orchestra in your life. Just imagine that when you see some beautiful things, or just imagine very simple things, when you see some objects, right? Let's say I'm showing you one bottle and one glass. And if I'll ask you, tell me, what are this object? And you can easily tell. But if you'll go back to the physics, because these are all physics, and what you'll see, only the rays of light is coming from this object and entering to our eye. And from the eye, it is reaching the brain, and the brain is processing, and then finally we see this object. Just imagine how the eye, the whole pathway from eye to brain and the brain, they are able to create something out of it so that we can see all this object. But you will see the basis behind it, only the rays of light. So you just think about it, how the things are happening, who is doing this job, right? So this is one part of the intelligence, which we don't understand until now. The second part is called the cognition. So just imagine how you feel about your existence and what is happening around you, right? So all these things are integral part of intelligence. And as a human being or as a researcher or scientist, we don't understand all this process clearly. That's why I told that most probably in next 15 years or 20 years, we might not see any real AI system. Whatever we are seeing today and whatever we are going to see, all the system would be, I can say, simple AI agent. Okay, the agent which are just created for certain purpose, but not like these agents can do all the jobs what you do as a human being. That's why I'm telling that it's not possible. And that's why this topic is very, very important in this context to understand how human brain process the information. So coming to this cognitive processing, the simple definition, this is I Google and I found this things that cognitive processing is a general term to describe a series of cognitive operations carried out in the creation and manipulation of mental representation of information. Then question comes, what are the examples of cognitive process? Okay, this is a little bit of, more descriptive. Cognition is a term referring to mental processes involved in gaining knowledge and comprehensions. These cognitive processes include thinking, knowing, remembering, judging, and problem solving. These are higher level of functions of the brain and encompass language, imaginations, perception, and planning. See, this is a very small paragraph, but in this paragraph, there are many things are there which we hardly understand. That's why I thought that I'll just highlight some of the problems, because you know that many people are interested in cognitive loading or cognitive processing, right? Even here also I would like to highlight few of the things. If you are interested in this domain or if you wish to pursue a career, definitely this is a very, very interesting domain, and the future also lies here. So you know that many, I think 10-15 years back, Government of India identified that in addition to different pillars of our society, the cognitive science is one of the important pillar. So we need to take the headway in this domain so that we can solve some of the problems both in the health and engineering. That's why my suggestion would be to get the right kind of training, that how you can measure these cognitive functions, and based on that, based on your understanding, how you can manipulate the brain, as well as how you can develop the next generation technology, all lies on your understanding. So even in the internet also you'll find many papers, actually when I go through all this paper, I found, many of the paper, more than 50% of the papers are conceptually wrong. And even I'm telling you, some of the IEEE papers and some of the very, very top-notch journals. So that's why this is a FDP program, one kind of faculty development program, and I know that many faculty are attending this talk. So please be aware when you are working, first check that whether this work, even if it's published, but it does not mean that this is the best work or this is the right kind of work people have done. So you have to check the quality of the work, the people that you are involving in this work, what is their expertise, what is the training, and all this depends, and all that will drive you that whether you should read the paper or not, right? So in that way you can get the right kind of knowledge when you are learning and when you are going to do some of the important you are going to solve some of the important problems in this domain. So here let me show you one video. You can see here, let me see whether it's working or not. Just 1 second, let me. Oh, yeah, now you can see the video. Oh, I don't know why it's not working when I'm making it full screen. Yeah, you can see. So in the left screen, I'm showing one video, and in the right screen, so I don't know in the full view, it's not coming. Okay, so basically what I'm showing you here in the left panel, you can let me just here. You can see in the left screen I've written presented clip. In the right side I've written clip reconstructed from brain activity, right? So in the screen, so actually when you are seeing this video, let's say I'm recording your brain picture or the images of your brain, and from this brain picture I'm trying to reconstruct the object or what you see in this video, right? And this is one kind of mental process. Let's say any kind of process. So the question is, can I reconstruct, right? So basically what you are getting some of the activations from the brain, some of the activations from the voxels of the brain, and from there the scientist or the researcher are recreating this sense. And it has huge applications when you are talking about any kind of, let's say, person who is in coma, or you want to understand somebody's brain, and you can do this. This is one kind of cognitive process. So for that, you need to understand the architecture of the brain and which part of the brain is responsible for what kind of job, right? So here in this picture, I'm showing you that as a human being, we do many things each and every second of time. Okay, maybe some of the jobs we do parallelly, some of the job we do sequentially. So so whether say we are listening or talking to somebody, whether we are interacting with some digital devices, whether we are writing, so each and every job require higher level of cognition. But the question comes that what do you mean by then cognitive load? So when you are doing this kind of cognitive processing or cognitive job, that time if any kind of uh, interruption will come, or any kind of, let's say when you are processing this kind of stuff and you are getting some kind of hindrance, right? And in the layman language, I can say this is a cognitive load. I'm getting some kind of load. That's why this is a definition from the internet. Cognitive load relates to the amount of information that working memory can hold at one time. So in our brain, when we process something in the brain, we coined few terminology: short-term memory, long-term memory, working memory, sensory memory, and all this terminology is very, very important in terms of processing. That means here you can see here that cognition is a brain process, right? So in order to do this brain processing, so you know that there are smaller unity there where the information gets stored. So when the brain process and the brain create something out of it, this is called the mental manipulation, right? If I'll define the working memory here, working memory is based on some information, we manipulate that information and we present some kind of output, and that happens in the working memory. So if I'll talk about the short-term memory, I know that, I assume that all of you know all this terminology. Short-term memory is basically, let's say I am going to visit one of my friend's house, and my friend told me, I'm driving, and my friend told me, okay, this is the address of my home, and you follow this path Okay, so when he will tell the address of his home, I'll keep in my mind. And the same time also, I'm listening to him, whatever the instruction he's giving. And this is called my short-term memory, right? And if I'll talk about the working memory, so let's say I got all this information and I created a mental map out of it. Okay, so that I can say, and that so that I can reach the destination on time and according to the instruction given to me. This is, I can say, this is working memory. So short-term memory and working memory, they are not same, but it looks very similar. And I can say short-term memory is part of working memory, right? So here, this cognitive load is the amount of information that working memory can hold at one time. So Schweller, who is a famous scientist in this domain, and since working memory, I mean, he has mentioned that since working memory has a limited capacity, instructional methods should avoid overloading it with additional activities that don't directly contribute to learning, right? So here this is the challenge. And based on this, if we understand this cognitive loading process, then we can simplify many of the process. Let's say if I'll give an example, let's say some mentally, I can say the neurodevelopmental children. I mean, those who have developmental neural problem, like you can say dyslexia, you can say autism. So for them, can we create some kind of interface which will help them to learn the things without overloading them? That means, can we simplify the process? Can we simplify the cognitive loading problem? Because they have certain different capacity, and in order to build the capacity, we need not to overload with many things. Rather than we can simplify it and we can help them in learning, right? So that's why you need to understand a little bit of memory architecture, how it works in the brain. So that's why it's very, very important to understand the neural correlates of it. So in this picture, this is again a picture I've taken from internet. So here I'm just showing you that when the information comes, okay, then the information comes through some sensory pathway, whether it's the visual, auditory, tactile, or olfaction, or test. I mean, these are the all five sensory modality what we have, right? And when it comes, whether it would be, I mean, store as a sensory memory or you can forget, right? Then you have the working memory, and then finally you have the long-term memory where encoding and retrieval happens, right? Um, so again, already I talked about, I told you the working memory. Working memory, it operates over a few seconds. This is also consists temporary storage, then manipulates information, and then focuses attention. So the biggest job is of working memory is to manipulate different kind of information. And already I highlighted this three kind of memory: sensory memory, short-term memory, long-term memory. So sensory memory is very, very important kind of memory. And now the technology is advancing day by day. So even the sensory kind of memory, I mean, this kind of concept we are using in the IoT kind of applications. So sensory memory is basically when you get all this information through different your sensory input channel, and then, as I told you, that you remember some of this thing and you also forget. Let's say smell of mango, right? It's already encoded in your brain. This is, I can say, one of the sensory memory. Likewise, there are n number of sensory memory. So like short-term memory. Short-term memory is also the memory which you need for that short amount of time, and you might forget, right? But long-term memory, which you keep it for a long time. So based on their origin, based on the type of job they do or accomplish, and the architecture, we divided this memory into different kinds, right? So again, the long-term memory is divided into explicit, implicit, and explicit again divided into few kinds, and implicit again divided into few kinds. So that you can study if you will Google, and you will get many papers on this memory. I'm not going into it. So then finally, we create the schema. So schema is basically, again, this is again another architecture of cognitive processing. And it is, again, you can see here, in this picture, I'm showing you personal schema, social schema, self schema, and event schema. That means from this memory, from all this kind of event, we create this kind of cognitive architecture. And depending on that whether we need to store as a short term or long term, and this is what we adopt, right? So there are many different kind of theories are given for this to assess this cognitive load. This explains the relation between the human cognitive architecture, instructional design, and learning. So two main constraints for this kind of cognitive problem, one is called the cognitive load and another learning. So as I told you that if will increase the cognitive load and the learning will not be efficient. So you have to compromise, or these are all handshaking kind of approach. So which one you have to focus, and what is your basically what you aim for, right? So the major factor in determining success of an instructional intervention is called the cognitive load. So that's why for any kind of nowadays when people are working to develop some kind of learning material, they always focus on the cognitive load. So let's say if I'll show you some of the text when you read, you feel very, you enjoy reading the text, right? But some of the text you feel, oh my God, what I'm reading, and you will feel that your brain is going to burst, right? And this is called the cognitive load. So the question is, why some of the text is very soothing or very enjoyable when you are reading, whereas some other texts they don't, right? So these are the things you need to understand, and then you can create many kind of learning material. So this cognitive load is also, not only focused or not only limited in this learning problem, but also in many other domains. Let's say if I'll talk about cognitive architecture. Cognitive architecture means these are all very new kind of things are happening nowadays. Cognitive architecture means, let's say, when you see some buildings, right? When you see some building, you feel very good. Yo, this building looks very nice, looks very good. But when you see some buildings, you feel suffocated, right? Oh my God, what is this? This is this the real architecture? Okay, so the brain, because you know that only one thing which don't lie, your brain, right? Let's say when you tell something, okay, let's say when you are lying, but people ask your brain only tells the truth, right? That's why this cognitive processing plays a very, very vital role, not only in learning, but also many other domains, including this cognitive architecture. So that's why this multidimensional construct representing the load that performing a particular task imposes on the learner's cognitive system. And we divided this kind of cognitive load into two types. One is intrinsic, another is extraneous, and third is German. German is basically the combination of this intrinsic and extraneous. And then this is one kind of hybrid kind of load problems, right? So then here the question comes, uh, what if the cognitive load that is intrinsic and extraneous combined exceeds the working memory? What will happen? What will happen? Now the capacity of information processing is compromised. And if the capacity of information processing is compromised, then learning will be automatically compromised. Okay. So the second question is, what if the total working memory load is excessive? Then again, learning is compromised. The chance of useful changes to long-term memory is reduced, right? So accordingly, when you are planning to develop some kind of intervention technology, then you need to understand all this process very well. So instead of developing some of the key technology, uh, my advice is always to understand the neural processing or the cognitive mechanism, and based on that, try to develop some of the technology. So here, as I told you, the cognitive load is basically when the cognitive processing is getting interrupted, right? Or getting obstruct. Then we say that this is a cognitive loading kind of problem. So here, to understand, then definitely this is what you need to do. You need to understand the whole brain, that how brain work. And to understand the brain, you know that the brain is made up of billions of neurons, which are the building blocks of our intelligence. This neuron, through their electrochemical process, the sends the information, and receives the information, and finally organize beautiful orchestra in our life. So when you talk about that, why we are interested, all are interested in science and technology, then two things comes to our mind. One is we are doing science and engineering to make our life comfortable, right? And we do science and engineering to understand the beauty of this universe. But interestingly, people compare the universe with our brain. These two things are very much similar. So you can see here, I'm showing you the galaxies in this universe and the neurons in the brain. They look very much similar, right? And if you look at the brain cell and the universe, they are very, very similar. That's why to understand the beauty of this universe, uh, so you can look at the sky and try to understand. But before doing this, what you can do, you can look at your own brain to understand the many hidden mystery, right? And how you can do this? In order to understand the beauty of this brain, you have to take three kind of approach. What are those? One is to understand how a normal brain functions. That means, let's say if your brain and my brain, they're normal, how they are functioning, right? Second is to understand how the brain develops. That means after the newly born baby took birth, then how the brain is developing. And third is, if the brain is affected with some kind of problems or disorder, what is happening to the brain? So why I told these three things, because any kind of problems you take in the domain of intelligence, first of all, you have to work on these three kind of brains. Then only you can answer some of the questions, right? Even I'm telling the some of the question, not all the questions. That's why you need to study these three kind of brains. Even if you are talking about cognitive loading, you need to understand these three kind of brains, how they are behaving, right? So that's why I've written a defining big goal. So here I'll highlight two of the very simple problem, and you can extrapolate those problems to your cognitive processing or cognitive loading kind of work. So here I'm showing you very interesting study which my lab took. This is a very recent work. I'm showing you neural correlates of perceptual groupings in brain. What does it mean? You know that object recognition is a very, very interesting terminology, and not only terminology, but also it has huge application in many things. But the interesting thing is that, do we understand how brain processes this information, and how brain understand, or how brain try to find out the pattern out of it, right? So let me change my slides a bit, and then I'll show you again the slide from actually, okay, some of the slides from my object recognition slide. Then I'll come back here again. Just 1 second. I hope you can see my another screen, completely black and white screen, right? Can you see?
Yes, sir. Yes, sir. We can see your screen. So
Okay. So here, okay, I'm not going to talk about the object recognition. I'll just talk about very interesting things. Okay, let me go to that slide, and then I'll continue from there. Okay. Uh, okay. Yeah. So here I'll talk about what is the nature of processing underlying recognition, whether it's a feed forward or iterative via feedback. Um, because this kind of information is not well understood. So it's very, very essential, because it will help how can we make inferences about the flow of information within a black box. So if we'll try to understand the speed of processing, that might yield some interesting clue. So here there are some information you can see here. The maximum firing rate of cortical neurons is approximately 100 Hz. That means the cortical neurons fire at the frequency of 100 Hz. That means an action potential every 10 milliseconds. Okay. So that's why we need at least 10 milliseconds to determine the rate of firing of the neurons. So if we talk about the latency of V1 neurons, this is about 70 milliseconds, right? So the thing is that if we observe evidence of object recognition in neural responses after X millisecond, then the number of intervening stages means through how many stages the information get processed so that finally we perceive something. Okay, so this is called I. So here I I equal to x minus 70 by 10. So 10, already you know that the frequency of the neural frequency firing rate, and 70 is the V1 neurons when they respond, and x is the time taken, millisecond, right? So if x is small, then the processing is likely to be largely feed forward. Otherwise, there may be a scope for iterative computation. So what is x? So there is a paper from 1996, and this paper is very, very interesting paper and published in Nature. So they talk about that when we see some animal or non-animal images, whether this is a feed forward or the iterative process, it passes through some iterations. Okay, and so they conducted this study. This is, you can see here, the brain. I mean, the EEG is being collected using this 128 number of channels. Okay, electrode, and then you can do some kind of ERP analysis. After collecting the EEG, you have to do the time logged averaging, and then finally you can get this ERP plot. So in this picture you can see in this brain from each and every region, and let's say few sensors are being shown here, and these are the ERP plots. And from this experiment, from this animal and non-animal experiment, what they found that around there is an evidence of image discrimination by 150 millisecond. So you will see in this picture, there is a divergence. So you will see the black bold line, this is for the animal, and the light line is called for non-animal, and there is a difference. Difference is little bit of darker. The upper one, you can see the upper one, my cursor, you can see this is the difference. So that means the divergence started appearing around 150 millisecond. That means here the brain is able to differentiate between animal and non-animal, right? So then here my x is 150 millisecond. So here, if I'll try to calculate the intermediate steps through which this process happens, then what I'm getting, I equal to 150 minus 70 by 10. This means 8. So given that there are about 5 neural links between V1 and the frontal cortex, this suggests that it's a feed-forward processing, right? So in order to understand this mechanism, what we did, I'm going back to my original slide. In order to understand this process, what we did, I'm showing you here. In order to understand this process, we conducted one experiment here that what is the neural correlation of the perceptual grouping in the brain? So here just I've written that the human have the ability to discriminate between objects with great accuracy. However, the neural basis of perceptual grouping to identify objects is still largely unknown, irrespective of significant research effort. So here you can see here in this this is the experimental design. Okay, so on this slide you can see in the left side you can see these are some structure. It's written structure, and in the right side it's written non-structure, right? So structure means, let's say these are all random dots. In this random dots, in some cases the dots are aligned and looks like a line, but in other cases this dot, it does not look like line. Okay, so the question is how your brain is able to see a line in case of structure. That's why we call it structure, and in the other case it's not able to see any line. Okay, and this is one example of perceptual grouping, how perceptually we group this and we feel that this is a line. And when we presented this kind of stimulus to the subject and we recorded the brain signal, and not only we recorded the brain signal using the EEG 64 channel EEG, also we recorded behaviorally. Behavioral means, let's say if I'll present on a computer screen and I'll ask you, please press A when you see structure and press B when you don't see any structure. And then what we did, the response times, that how much time your brain is taking to respond, also we noted. And from this analysis, what we found, you can see this is a simple setup, experimental setup. And this is the behavioral results. Behavioral results means that how much time behaviorally somebody is taking to tell this is a structure versus non-structure. And this is a simple computer domain experimental paradigm. And we found that yes, mostly the average, we found that around 500 to 600 millisecond, everybody is able to tell that this is a structure or this is not a structure. But when we analyze the brain signal, what we found, so these are the signal you see from the, so you can see here in the figure A, this is the ERP results, figure A, these are the signal from the frontal electrodes. Frontal means the frontal side. And the lower one is the back electrode. You can see in this brain picture, it's highlighted. Okay. So we wanted to see that where the divergence is happening, how these two signals are getting differentiated in the frontal as well as the occipital lobe. So interestingly, what we found, you can see here in this picture also, in the frontal, in the back part, actually it is hitting the back part first, the occipital lobe, and then going to the, because you can see the time here in the x-axis is time. Okay, it's showing the divergence is happening early, even around 60 millisecond in the brain, in the occipital cortex. Again, this is the grand average ERP plots of all 15 subjects, and then we also see, we try to see that how the information is flowing from 20 milliseconds, 60 milliseconds, 100 milliseconds, and how it's evolving along the all timeline trajectory. So from these results, what we found, this suggests that the perception of grouping induce higher activation in brain as compared to the other stimuli. The ERP divergence potential for structure is evaluated in frontal, occipital, and V1 regions, which evidence that the brain can perceive structure in 60 milliseconds. Also, the flow of information from V1 area to the frontal area of the brain is seen for structure, which signifies the feed-forward processing in the brain for perceptual grouping. So here in this case, even, when I'm showing you the face versus object or animal versus non-animal, even the structure and non-structure, we found that even it is getting complex. Getting this whole process is happening is very quick, right? So here, if I'll calculate the iterative step, it will be very, very less. That means the process is completely feed forward in nature. There is no iterative, it is no iterative process is involved in this kind of processing. So why this is important in terms of understanding the cognitive loading? Because this is the example I gave you. It's a very simple example, right? And then with this kind of example, you can try to see that which are the network is evolving during the processing. And when you are going to add some kind of loading means whether it's a visual loading, whether this is a memory loading, whether this is a auditory loading, any kind of loading, then how it is going to disrupt this kind of processing mechanism. And if you find, or if you try to see the disruption, then you can accordingly see that how much information or how much load somebody's brain can take, because this loading problem is also very individualistic in nature. So that means if you will develop a system with some kind of loading, it might not, work 100% for all the people. But yes, let's say if you have done your experimental paradigm and if you have validated with, let's say, 100 subjects, and if you have already kept some kind of tolerance, right? Then that might work well, let's say 70 to 80% accuracy. So for that, you need to understand all this basic mechanism. Okay, so I'm going to show you another very interesting example of cognitive problem called the spatial imagery. Spatial imagery is also a very, very interesting problem, not only in the domain of cognitive loading, but also in the domain of understanding intelligence, when we all are interested in artificial intelligence, right? In order to understand this problem, so I conducted a research many years back, around I think in 2014 or 13. So that time, my interest was to understand how this spatial imagery develops, or So, okay, before telling about the spatial imagery, let me give a very simple example so that you can understand. So now all of you are attending my talk. And now if I'll ask you, just try to visualize how your mom's kitchen, how it looks like. And you can do it very well, right? And if I'll ask you, just think about how your study room looks like or how your office looks like. You can close your eye and you can see it, right? Let me give another example. Let's say now you are attending, let's say um, you visited Kolkata and you have visited, let's say, the zoo, and where you stay, from there, you know in which way you have to go to the zoo, right? And if I'll ask you, just close your eye and imagine in which route you went to zoo. You can do it easily, right? Just imagine if you are not able to do this task, what will happen to your life? You'll feel that, oh, I'm going crazy. I'm going completely mad, right? This kind of things will come to your mind. So this is a very, very efficient ability what we have. And this spatial imagery also, this ability also makes us intelligent. So I thought that, okay, let's, do some kind of study to understand. And I did a very simply, very, very simple kind of approach. So please remember, always, I tell, wherever I deliver talk, I tell the same thing. And here also I'm telling you one thing. So always, even if the problem is really very big, it requires very simple solution. So sometimes, being an engineer or scientist, what we try to make our problem very complicated. The solution very complicated. And science and engineering are very, very simple, but we unnecessarily make it complicated. So please try to answer the question in the simplest way possible. So here in the spatial imagery also, I'm showing you very interesting study I conducted. This is, I found through, coming across some literature that the blinds are compromised with this kind of ability, that blinds are not good in spatial imagery. And also I found that, yes, there are many articles in this domain and everybody reported the similar kind of fact. So one question came to my mind, that which kind of perceptual ability or sensory ability step up this cognitive skill, step up this important cognitive skill in our life. So age that time, age also actually I do lots of work on the blindness. This why I thought, let's say if somebody, age, the researcher says that the blinds are compromised with this ability, and let's say today somebody is blind and tomorrow I can help him to see this world, or let's say I restore the sight to this blind person, and then whether the blind can again develop this spatial imagery ability or not, right? This question came to my mind, and I said, okay, let's try to understand that whether they can develop it or not. So what I did, I went to a nearby shop and I purchased some kind of toys, the child's toy. You can see, you must have seen in your home also, right? So here in this toy, I created some kind of matrix, 2 by 2, 3 by 3, and 4 by 4 matrix, right? And then what I did, you can see here in this picture, I'm showing you one, actually the blindfolded boy, he's a normal child who can see. And the right side picture is a blind child, okay? So what I did, I asked them to imagine, I asked them to touch it, even this, the normal child also has not seen what I have given him, right? I asked them to touch it just by hand, and they touch, just like you can see, the blind child will explore that, then he can say, okay, there are 2 by 2 kind of knobs are there, or somebody can say 3 by 3, something like that, right? And the similar way, the normal child also should touch and tell. Then what I did, actually, in order to do my experiment, little bit of tricky, I created this 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, because uh, it will increase the complexity. And another thing is that this is the command level. Command level means, you can see, command level means, let's say now you have not seen what I made on this grid, and you are blindfolded. Let's say you can see, but I have make you blind now. I have made you blind, and then what I'll do, I'll give you this 4 by 4 matrix to your hand, or 3 by 3 matrix to your hand, and I'll ask you, just touch it and feel what is this and how all these knobs are placed. Then you can feel it and you can say, okay, now I understand. Then what I'll do, I will remove this grid from your hands reach and I'll tell you, please follow my command. Follow my command means, let's say, you know that whatever I have given you to touch, let's say this is a 4 by 4 matrix, right? And I'll ask you, just imagine that you are sitting at 1, 1 coordinate. That means you are sitting at the corner, right? And I'll ask you, just follow my instruction and move, jump from one node to another node. I'll give a command like move one step right, move one step up, then again right, then one more right, right? And finally, what I'll do, I'll give you this grid again to touch and I'll ask you, tell me where you are now. And if the person will say, you can see my cursor, I think. And if the person will say, um, uh, let me point ledger cursor. Okay. If the person will say, I am here on this knob, then answer is correct. If the person will say, no, I'm here, then answer is wrong. Okay. So here you can see, if I'll do this kind of activity in 2 by 2 matrix, it will be very simple, right? Because only 2 or 4 knobs are there. If I'll do 3 by 3, little bit complicated. And 4 by 4 is again a little bit more complex, right? You know, in terms of remembering. And at the same time, you can increase the command chain. In this picture, you can see the first command chain is 4 level command, second is 5 level command, third is 6 level command. So if you wish to increase the complexity, you can increase the number of commands so that because the person has to remember and jump in the mental picture. When I conducted this kind of test on the blind, as well as the normally sighted people with blindfold, I got this kind of result, right? This is a 2 by 2 matrix, 3 by 3 matrix, and 4 by 4 matrix. You can see individually, this is 2 by 2, and you can see this is the command chain. I have introduced two things, two variables. One is the number of command and the matrix level, matrix 2 by 2, 3 by 3, 4 by 4. So what you can see, blind and sighted, initially for 2 by 2 matrix, and this is almost similar. There is not much difference except the command chain when I'm increasing the number of command. Again, in 3 by 3 matrix, though a little bit difference there, but not much. But in 4 by 4 matrix, you can see all are significantly different. I mean, that means the blinds are doing very poorly in this kind of task compared to their normal control, normal subjects, right? That means I am also get convinced that yes, blinds are compromised with this kind of skill. Then what I did, I restored sight to the blind. That means the blinds, those who are not able to see, they can see. And then after 4 months of their sight restoration, I conducted the study again. And this is only with the blinds. So that means I compare here, the white bars are pre-operative. Pre-operative means before the operation. And the black one are after the operation. Okay. So you can see here, there is a huge difference. Even in the 4th level, 4 by 4 matrix, that means after the sight onset, the blinds are able to develop this kind of concept, this spatial imagery concept. So from this study, what I found, that definitely vision plays a very, very important role in shaping up of our cognitive abilities, right? And this is one kind of learning, cognitive learning, right? But here there is a very interesting question comes that what is the pathway? What is the neural circuitry? Can we understand this mechanism? And see, this is a very, very simple experiment, and I published in Psych Science. This is also a top-notch journal in understanding the brain. So that same year, this work appeared in MIT News. That this is a very strong kind of results. I mean, see, this is a very, very simple kind of study. I have not used any kind of sophisticated equipment. Maybe some of you are thinking that only you can do brain research when you have EEG, fMRI, and all these kind of things. No, not at all. If you have a simple computer or a laptop, you can do world-class research if you understand the concept well, right? So this is what I found. And then the same year, two scientists got Nobel Prize on those who are working in the neuroscience, and they found the navigation cell in the bat, that when the bat navigate, which is the grid cell responsible, and for that they found that cell and they got the Nobel Prize. And that's a cell. I mean, they conducted many studies and found. But that year, MIT chose that this is one of the best research because this also talks the similar kind of things, but this is behavioral findings, right? But the most interesting thing would be, so what I came up with this conclusion that yes, the blinds, though they are compromised with this kind of cognitive skill, but with the sight restoration, they can develop this skill. So my question comes, let's say if you are as a normal human being, you must be, I mean, for the skill, you must be using some of the neural architecture, some of the neural pathway, right? So whether when the blind can see, whether they're using the same pathway or they reactivated the another pathway. This is not known to the whole scientific community. So now actually in my lab, this is what we are trying to understand, that which is the pathway. And if we can understand this mechanism well, so we can create the cognitive architecture. And this kind of, I mean, again, edge in the domain of cognitive, this spatial imagery, and spatial imagery is again another part of learning problem. And then cognitive loading is also coming into effect of this kind of things. So that's why you need to understand all the neural mechanism of all these fundamental processes, right? Um, just like I was talking about, I also highlighted another terminology called the sensory memory. So in order to understand this sensory memory, first of all, you need to understand how this integration of senses happens across across all the senses happens in our life to create all this beautiful orchestra in our life. Let's say when the child is holding this mobile phone, how the child is able to predict from this visual appearance of an object that how it feels to touch. That means when you're touching, you can also imagine or you can visualize how the things looks like, how the child is doing, whether this kind of ability is innate or uh, they learned it. That means whether it's a nature or nurture. So this nature and nurture is a very big debate in the domain of science, right? So that means which are the ability we are born with and which are the ability we learn through our experience and which are the ability we are a little bit, I mean, we are with and we are born with and then it get modified. So these are all very interesting questions we need to understand, right? So here for this question, actually, also we have a certain amount of studies on these issues. Um, so I'm not going into details of all these big questions. Here, what I'm going to tell you. So when the child is holding this mobile phone, uh, and when he's touching the mobile phone, we are getting some kind of haptic features from the fingers, and these are all time domain features. And in the same time, when he's looking at, he's also getting some visual features, let's say visual to VN. And then what is happening from this time domain, this dynamics of these features, the brain is somehow able to establish a map between all the septic features to the visual features. And based on this, the recognition happens, right? And these are all very complicated mental process. And you need to first understand all this complicated mental process, and then you can take the right step to develop the right kind of uh, uh, platform for the learning, mitigating the cognitive load problems. I hope that you could, I mean, you are able to understand some of the basic concepts. And yeah, I mean, there are many things also can be discussed, but I'm really sorry. Actually, in online talk, it's very difficult to continue more than 1 hour. So I'll be forced to stop here. But at least I wanted to give you some of the fundamentals in learning and understanding the neural mechanism. And if you can understand, you can do wonders. So many of our research are appeared in Science magazine, also the cover page Science, Nature, Times magazine, Harvard and MIT News. This is what I was showing you, the MIT News. Vision is key to spatial skills, and it got highlighted when I published this work. As well as in many papers, Hindu, this is the Wall Street Journal, and one Geo magazine from Germany. So they covered some of the stories from my lab at IIT Delhi when we work with some of the blind children after the sight onset, and how the brain is understanding different perceptual stuff, right? And also Netflix is also making one documentary from my lab um, about how we start recognizing different things. And if you can do this kind of work, I mean, fundamental work, you can have truly a very big impact on your society. So some of the work, what I've shown you, we restore sight to the blind, and we have restored sight to more than 700 blinds in India. And based on that, we try to understand how brain processes the information. And based on that, we try to develop technology for some other kind of neural disabled children, like autism, dyslexia, like that. So here I hope that I convey the main message or main motto of our doing research, that to have right kind of impact on your society. And only you can do that when you understand the fundamental concepts behind it. Thank you very much for your time. And if you have any questions, I'll be happy to answer your questions.